The most effective way to think is to understand the principles better. Over the next 122 years, I will help you break down knowledge. I will explain the operating mechanisms behind various structures. Today, I plan to give you a comprehensive understanding of wind turbines all at once, from the blades, yaw, pitch, main shaft, gearbox, brakes to the generator, and the complete workflow of voltage transformation and transmission. Have you ever wondered why the blades of a wind turbine spin so slowly? It can ultimately power thousands of homes. Many people think wind power is just the wind turning the blades, and the generator starts generating electricity. In reality, it's not that simple. The challenge is not just getting the blades to spin, but more importantly, converting the unpredictable and variable nature of wind into stable power that the grid can accept. Because the wind is chaotic, but the grid cannot be. Let's first look at the most intuitive part of the wind turbine. A fan uses electricity to turn the blades and push air, while a wind turbine does the opposite. It relies on air to push the blades to spin, then converts that rotation into electrical energy. Modern large wind turbines almost all use a 3-blade design. Why not 2 blades, or 4 or 5? 2 blades are cheaper and can make money faster. But the problem is they create more vibration and noise. The impact on the tower and drive system is also more intense. More blades lead to smoother operation, but the weight, cost, and structural complexity increase significantly. 3 blades strike a balance between efficiency, stability, noise, and cost, which is why most large turbines use 3 blades. It's not just a designer's preference for symmetry, but an engineering compromise. These blades are enormous. Modern turbine blades can reach lengths of several dozen meters, even exceeding 100 meters. They cannot be made from solid metal like regular fan blades, because that would be too heavy. Turbine blades are usually made from composite materials like fiberglass, carbon fiber, and resin, which are lightweight, yet can withstand long-term bending, vibration, thunderstorms, low temperatures, and millions of rotations without fatigue. But the most critical aspect of the blades is not their size, but their shape. Turbine blades resemble elongated and twisted wings. Their cross-section is not flat, but irregular. As wind flows over the upper and lower surfaces of the blades, the speed and pressure differ, generating lift. Note that this lift is not in the direction of an airplane taking off, but rather a force generated by the blade structure that causes the hub to rotate. In other words, wind turbines do not rely on the wind directly hitting the blades to spin, but rather utilize aerodynamics to convert the wind's kinetic energy into continuous rotation. This is also why the shape of the blades varies from the root to the tip. The area near the hub is thicker because it must bear significant structural loads. The closer to the tip, the thinner the blade becomes, as the tip moves faster and needs to reduce drag and noise. Counterintuitively, the blades are also twisted. This is because the speed of movement varies greatly at different positions along the blade. The area near the hub travels a shorter distance per rotation and moves slower. The tip sweeps a huge circumference, moving very fast. For the blades, the wind they experience is not just the natural wind, but also the relative wind generated by their own rotation. Near the hub, the relative wind is smaller, while at the tip, the relative wind becomes much stronger. If the angle of the entire blade were the same, the tip would easily create turbulence and significant drag, which would not only reduce efficiency, but also cause vibration and structural stress. Therefore, engineers design the blades to have a twisted shape, allowing each part of the blade to face the wind at a more suitable angle. This is why turbine blades seem simple, yet are actually very precise. They are not just 3 large sticks, but 3 massive aerodynamic structures. However, no matter how well the blades are designed, there is one prerequisite. They must be aligned with the wind direction. The wind does not always blow from the same direction. If the turbine is misaligned with the wind, the energy captured by the blades will decrease, and it may even increase unnecessary loads. Therefore, wind turbines are equipped with an anemometer and a wind vane at the top. The anemometer measures wind speed, while the wind vane determines the direction from which the wind is coming. Once the control system detects a change in wind direction, the yaw system at the top of the tower will activate, and the yaw drive motor will slowly rotate the entire nacelle through a large ring gear, realigning the blades to face the wind. You can't see it moving, because it turns very slowly, but it has to move a nacelle and rotor system that weighs hundreds of tons. It's like giving the wind turbine a steering wheel. It doesn't wait for the wind to come, but actively turns to a position that is better for capturing the wind. Next, let's talk about the pitch system. The blades are not fixed to the hub. Each blade's root is connected to the hub, with hydraulic cylinders or electric actuators inside that can slightly adjust the angle of the blades along their long axis, changing the angle of attack. When the wind speed is appropriate, the blades adjust to a more favorable angle for energy absorption. When the wind is too strong, the blades will turn to a feathering angle to reduce wind capture and protect the entire system, which is crucial. A wind turbine does not perform better with stronger winds. When the wind is too strong, the power generation efficiency actually decreases, which may put the blades, main shaft, gearbox, and tower under dangerous loads. Therefore, modern wind turbines need to constantly adjust the angle of the blades to strike a balance between power generation and protection. Once the blades convert wind energy into rotation, the force is concentrated on the hub, which is the connection center of the 3 blades. The hub is also the starting point of the entire rotating system, usually covered with a streamlined nacelle. This allows the airflow to smoothly bypass the central area, reducing resistance. The nacelle is located behind the hub, as seen from the ground. The nacelle looks like a small box, but up close, you'll find it's actually quite large, containing the main shaft and gearbox. It also houses the brake, motor control system, and cooling system, functioning as the mechanical heart of the wind turbine. After the wind pushes the blades and hub to rotate, the main shaft also turns, but there's a problem. the main shaft rotates very slowly. The blades of large wind turbines may only make a few dozen rotations per minute, which already looks impressive. But for a typical generator, this speed is too slow. Generators usually require a higher rotation speed to generate electricity effectively. Therefore, a gearbox needs to be connected behind the main shaft, which converts the slow, massive torque into faster rotation. For example, it can increase the speed from a few dozen rotations per minute to over 1,000. You can think of it as a reverse-acting transmission system, where the blades provide slow, heavy power. The gearbox then converts it into fast rotation suitable for the generator, but high-speed rotation also brings risks. If a storm occurs, the blade rotation speed can spiral out of control, potentially subjecting the entire drive system to huge shocks. Therefore, a braking system is usually set up near the high-speed shaft for emergency shutdowns. Hydraulic clamps will tighten the brake disc, locking the system. However, when a real wind turbine shuts down, it doesn't rely solely on mechanical brakes to hold up. The system first adjusts the blades to a feathered angle. This minimizes the wind's push on the blades, and then the braking system completes the locking. Otherwise, relying solely on mechanical brakes against strong wind pressure would be very frightening. The high-speed shaft continues backward. It reaches the generator, whose basic principle is to convert rotation into electrical energy, with a rotor and stator inside. The rotor spins with the shaft, while the stator is the fixed part, and the magnetic field between the rotor and stator constantly changes. This generates current in the coils. At this point, it seems that wind energy has been converted into electricity. But the real trouble is just beginning, as the grid has very strict requirements for electricity. It's not enough to just generate some electricity to connect to the grid. The grid has specifications for voltage, frequency, and phase. For example, some regions require the AC frequency to be stable at 60 Hz, while others require 50 Hz. However, wind speed is not stable. It varies, causing the blade rotation speed to change as well. Changes in blade rotation speed will lead to changes in generator speed, and when the speed changes, the output frequency may also vary. This is one of the trickiest aspects of wind power generation. Wind is natural, while the grid requires it to be as stable as a machine. To address this issue, many large wind turbines use doubly fed induction generators and power electronic control systems. Simply put, the generator does not just passively follow the shaft's rotation. The control system injects controlled current into the rotor coils. This creates an adjustable magnetic field, so even if the mechanical speed fluctuates, the system can compensate for some of the differences through electromagnetic control, making the output power closer to grid requirements. If the wind weakens and the rotor speed decreases, the control system will supplement a bit of current. If the wind strengthens and the rotor speed increases, the control system will make a reverse correction. Its role is not to stabilize the wind, but to convert unstable wind into more stable electricity through the generator and control system. This is the true brilliance of modern wind power. It's not just about making the blade spin. It also transforms highly variable natural inputs into standard outputs that the grid can accept. The generated electricity cannot be transmitted over long distances directly. The voltage output from the generator is usually not suitable for long-distance transmission. If the voltage is too low, the current will increase, leading to higher line losses, and a lot of energy will be wasted as heat. Therefore, electricity is sent down through thick cables inside the tower to the ground, then into a transformer. The transformer will increase the voltage, and with the higher voltage, the current can decrease at the same power level. This significantly reduces transmission losses, and the electricity then enters the substation, ultimately connecting to the grid. It is then sent to cities, factories, and homes. So when you see a wind turbine, it may seem like just 3 blades slowly turning in the air, but in reality, the energy transmission path is much more complex. The wind is first captured by the special shape of the blades, converting it into the rotation of the hub, while the yaw system aligns the nacelle with the wind. The pitch system controls how much wind the blades absorb. The main shaft transmits the slow, high torque to the nacelle, and the gearbox increases the speed. The generator converts rotation into electricity, and the control system corrects the unstable input into a grid-compatible output. Finally, the transformer boosts the voltage and sends the electricity out. But if you only see it as a pile of parts, you still won't understand the true counterintuitive nature of wind turbines, which is to convert something highly unstable into something that must be stable. The wind has no switch, no fixed direction, and does not blow according to grid frequency. But wind turbines tame the wind step by step through yawing, pitching, transmission, the generator, and the control system. Therefore, wind power generation is not simply about the wind blowing the blades and the blades generating electricity. What really happens is that an invisible, elusive wind that fluctuates is converted into grid-compatible electricity by this several hundred-ton machine. What you see are just 3 blades slowly turning, but behind it operates a vast engineering system that converts wind into electricity. It is a huge engineering system that transforms wind into electricity.